We're talking about some different types of reactions. We talked about precipitation reactions. Now we're going to look at acid-base and gas evolution reactions. These are both types of reactions that can happen with a double replacement. So the analogy of the people coming to the party and swapping partners and getting involved works for these as well. We have the anion from one reactant combining with the cation from the other. So an acid-base reaction, also called a neutralization reaction, occurs when you have an acid reacting with a base and they neutralize each other. Water is the most common product in this, but it can be a weak electrolyte. A gas evolution reaction, evolution, producing a gas. So this is a reaction that produces a gas. It's often seen as a bubbling or a fizzing. We did a reaction where we dissolved copper in acid and we saw a brownish gas coming off. Okay, that would be a gas evolution reaction. So we need to talk a little bit more about acids and bases. There are several definitions of acids. The Arrhenius definition is that an acid is a substance that produces hydrogen ions in aqueous solution. So if we look at HCl, which we have learned to identify as an acid because it starts with an H. HCl, when we put that in water, it ionizes, it forms hydrogen ions and chloride ions. So that fits the Arrhenius definition. What's really happening here, though, is we're not getting free hydrogen ions floating around. So let's think about that. What is a hydrogen ion? What is a hydrogen atom? How many protons? 1. And how many electrons? 1. So if we have a hydrogen ion, H+, it lost its electron, what's left? Just a proton. So this is a proton. It's just a nucleus. So extremely small. I think of hydrogen ion, I've told you that hydrogen is like the baby brother of the family, gets away with violating all the rules. Well, the hydrogen ion is when it was a newborn baby, right? Do you ever see newborn babies out for a walk by themselves? Do they go to the park on their own? No, they're always with someone, right? Because they can't walk. This hydrogen ion is too small to be out alone. So it's not actually out alone. These reactions are happening in aqueous solution, meaning they're swimming in water, literally. So this hydrogen ion that is produced is going to get picked up immediately by a water molecule. The water molecule is just going to hold on to this hydrogen ion because you can't leave them laying around, right? Somebody's got to be holding them. So that makes this thing, okay? We call this the hydronium ion. It's a water molecule that's holding an extra proton, a hydrogen ion. So here we see some water molecules, and here's the hydronium ion. We often use H+ and H3O+ interchangeably, which is understandably confusing to students. Why do we do that? Well, H3O+ is what it actually is, but when we write it that way, it makes all the chemical reactions more complicated. And the water is just there. It's never really part of the reaction in this capacity, and so it doesn't have to be included. And so a lot of times we'll ignore that water is holding the baby, and we'll just focus on the baby, the hydrogen ion. So this acid, HCl, one molecule of this produces one hydrogen ion. Some acids can produce more than one. These are called polyprotic acids. Polyprotic, many protons, they release many hydrogen ions. So sulfuric acid is an example, H2SO4. It's called a diprotic acid because it has 2 protons that it can release when it ionizes. H2SO4, I just mentioned, was one of the strong acids. It is strong in its first hydrogen ion. It's weak in the second. And so what that means is when you put H2SO4 into water, it's going to immediately lose one of its protons and form that hydronium ion. And the other proton is mostly going to hang around on the sulfate ion and be a hydrogen sulfate ion. The Arrhenius definition of a base is a substance that produces hydroxide ions in aqueous solution. So sodium hydroxide, soluble ionic compound, when that dissociates, we form sodium ions and hydroxide ions. There are the hydroxide ions. This is a base. There are other bases, such as ammonia, that don't have hydroxide ions in them, but they still produce hydroxide ions by pulling a hydrogen off of water molecules. So what happens there is NH3 reacting with water. The hydrogen, the ammonia will take one hydrogen from the water, and then we'll have a hydroxide ion. There are some bases that can produce 2 moles of hydroxide per mole of base, and those will be things like barium hydroxide, because there are 2 moles of hydroxide. These do not dissociate sequentially like the diprotic or polyprotic acids, because they're soluble and they just come apart all at once. Mostly we can identify acids as being ionic hydroxides. So a metal with a hydroxide, that's going to be a base. So in an acid-base reaction, the acid produces hydrogen ions in solution, the base produces hydroxide ions in solution. It's the hydrogen and hydroxide ions that react. So we've got the hydrogen ion from the acid and the hydroxide ion from the base coming together to make water. So if we have HCl and NaOH, we're doing that swapping partners thing, where here we've got the hydrogen ion and we're going to pair it up with the hydroxide ion. Turns out there's a chemical reaction there, and that makes water. If you just swap the ions, you'll end up with H plus and OH minus, and if you treat that as an ionic compound, you'll write that as HOH, and you should say, that looks weird. That's H2O. What happens to the other ions, the chloride ion and the sodium ion? Well, we put those together to see if they like each other. Sodium chloride, and we think about the solubility rules, and that's soluble. So those are just hanging out in solution. The sodium ion, the sodium ion and the chloride ion did not actually participate in the reaction. They were spectator ions. So if we take them out of the equation, we get a net ionic equation of H plus OH minus forming water. And this is the net ionic equation for most acid-base reactions. So here we have an illustration. Pictures are always nice. So this is that same reaction, HCl and sodium hydroxide. So HCl is a strong acid, so it's going to ionize completely. We've got chloride ions, and we've got the hydrogen ions on water molecules. They're being held because they're too tiny to be out by themselves. So we've got these hydronium ions. And in the sodium hydroxide, it's a soluble ionic compound. We've got sodium ions and hydroxide ions. When we mix these together in this beaker, the hydronium ion and the hydroxide ion get together because they kind of want to be water. And the hydroxide's missing a proton, and the hydronium ion is carrying around this extra proton. And so here's this person carrying a baby and this other person who wants to be carrying the baby, and so they're like, here, you hold the baby, and then everybody's happy. And so that makes a water molecule. And what's left is the sodium and the chloride ions. They didn't react. They're just hanging out. So you mix sodium hydroxide and hydrochloric acid, which both of them, if you drank those, they would seriously injure, if not kill you. If you get them in the right proportions, you mix them together and you just get salty water. Literally, sodium chloride dissolved in water. They neutralize each other. So here's some common acids and bases, and here's where the book finally talks about strong acids. So here are the 6 strong acids. You just memorize those. There's only 6 of them, right? And these 3 are related to each other. Any acid that's not one of those is a weak acid. And there's a whole bunch of them. These are just some examples. So hydrofluoric acid, HF, is a weak acid. Fluorine is a sister of chlorine, bromine, and iodine. But she's the littlest sister, okay? So the acid that fluorine makes is weak. The acid that the big sisters make are strong. Here's acetic acid, which we should recognize because that's a hydrogen ion and an acetate ion. Would not expect you to remember this one or know this one, formic acid. That's the acid that California fire ants have. And when they bite you, that's why it stinks so bad. And here's some bases. For the most part, when we see bases in Chem 1A, they're going to be metal hydroxides. The one exception you need to remember is ammonia. So ammonia is a weak base. It's not going to look like a base to you, so you just have to remember, oh yeah, NH3 is a base. And I wrote it earlier, but it also shows down here. This is how ammonia produces hydroxide ions in solution. It takes a hydrogen ion from a water molecule, and the result is a hydroxide ion. So let's write equations for acid-base reactions. So they want a molecular and a net ionic equation for the reaction between aqueous HBr and aqueous LiOH. So they're being a little bit kind here and actually giving us the formulas. So we've got HBr, and we're told this is aqueous, so we don't even have to think about it. And LiOH, aqueous. I'm leaving a space there in case I need to write a coefficient. And we need to predict what the products are. We're going to do the same thing we did with the precipitation reactions. Here they gave me the formulas, so I didn't have to write the ions initially, but I want to write the ions out underneath. So HBr is H plus and Br minus. Lithium hydroxide is Li plus and OH minus. So then I'm going to swap partners and see what happens. So I'll just write them over here, H plus with OH minus and Li plus with Br minus. And when I put H plus and OH minus together, that's water. What's the state of water at room temperature? It's a liquid. It's a little silly to say that water is aqueous, because that would mean it's dissolved in itself, which is, yeah, silly. LiBr, equal but opposite charges, so we just need one of each ion. Soluble or insoluble? Remember the solubility rules? What's the first line? Lithium, sodium, potassium, and ammonium ions. Anything with those, always soluble. So this is aqueous. And then we need to make sure that this is a balanced chemical equation. Here's a bromine, there's a bromine, here's a lithium, there's a lithium, there's hydrogens all over the place. There's 2 hydrogens here and 2 there, 1 oxygen and 1 oxygen. This is my balanced chemical equation. This is the molecular equation. So we could refer to this as the ME, molecular equation. It also asks for a net ionic equation. So we learned how to write the complete ionic equation. You rarely actually need to write that all out. You mostly need to be able to see it in your head. You need to be looking at the complete ionic equation to find the net ionic equation. but we can sort of approximate it with our ion formulas here. So here I've got hydrogen ion. These are all aqueous, and so they would be shown as individual ions. This one, though, is a liquid, right? So we would not split that into ions in an ionic equation. So I'm going to maybe put a circle around that to remind myself, don't split those up. That's one thing. And here, this is aqueous, and so that's going to be split. This is an acid, but it's a strong acid. So this is the only thing that would not be split into ions in the net ionic equation. So then we can look and see, well, which of these ions are present on both sides? There's a lithium ion here, and there's a lithium ion on the other side. Lithium did not get involved in a relationship during this process. What's the other one? Bromide. So bromide came in hanging out with hydrogen, bromide leaves just kind of hanging out with lithium, but they're not in a relationship, right? So then we look at what's left. So we've got a hydrogen ion, and we've got a hydroxide ion, and those are going to react to form a water molecule. And we sometimes call this an NIE. Net ionic equation. Any questions? This reaction would occur in the same way as long as this bromide ion was something that formed a soluble compound, and the lithium ion. You could put sodium in there, sodium hydroxide instead. The reaction would happen exactly the same way. You could put HCl in here instead. The net ionic equation is exactly the same, because they were just watching. When you have two boxers in the ring and they're fighting it out, does the outcome of their fight depend on the specific people in the audience? No, it doesn't matter. It's the people in the ring. Let's do another one. Aqueous HCHO2, and they give us this big hint here, a weak acid, wink wink, and aqueous sodium hydroxide. We should recognize this as an acid because it starts with H. There are other ways to write that formula, but in general chemistry, we always write acids with the H first, the ionizable hydrogen first. So we've got HCHO2, aqueous. Now, if they hadn't told us that that was a weak acid, we should be able to predict that because it's not one of the 6 strong acids. And then we've got aqueous sodium hydroxide. And then we have to predict what's going to happen when these separate and switch partners. So swapping partners does not depend on whether it's strong or weak. We're still going to see if the partners exchange, because this is a weak acid, but it does ionize a little bit. And so there are hydrogen ions present. So this is H plus ions and CHO2 ions, sodium ions, and hydroxide ions. And we're going to swap the partners and see what happens. So we see this familiar thing happening again. We have the H plus and the OH minus. That's almost always going to show up in an acid-base reaction. And then we're going to write these other two. We've got Na plus, and we've got this CHO2 minus. Now that's not an ion that you have seen before, but it just follows the pattern, and so you should be able to deal with it. You take the hydrogen off, the hydrogen has a +1 charge. That means that the remaining ion has a -1 charge. And so when we stick these two together, we put the metal first and the other thing last. And when we put them together, we just look at their charges. That's going to be NaCHO2. Is that compound soluble or insoluble? Soluble. First line, sodium, lithium, potassium, ammonium. Anything with that in it is going to be soluble. So it doesn't matter that this is some weird cation that we haven't seen, anion that we haven't seen before. That one's aqueous. The H plus and the OH minus forms water. H2O, that's a liquid. So those are my products. And then I need to see if this is balanced. So I've got a sodium ion and a sodium ion. There's a carbon and a carbon. Here I've got 2 oxygens and 1 oxygen. That's a total of 3. And there's 1 oxygen and 2 oxygens. That's also 3. 1 hydrogen and 2 hydrogens, 3 hydrogens. 1 hydrogen here, and a hydrogen there, and a hydrogen there. Total of 3 hydrogens. So this is kind of a bit messy to look at, but it's balanced. Any questions? So that's our molecular equation, but that's not what they asked us for. They asked us for the net ionic equation. You kind of need to do the molecular equation first. Now we're going to look at these ions here, and before we start crossing out spectators, we have to ask ourselves, are these things that would be predominantly ions in solution? Here we have an acid, and the question we ask about acids is it a strong acid or a weak acid? This is a weak acid, which tells me that it's mostly intact molecules. So in the ionic equations, I'm not going to write it as individual ions. So those guys are going to stay together. This is an ionic compound that's aqueous, so those separate into ions. This is an aqueous ionic compound, so those separate into ions. This one has a state symbol L. If it's Lg or S, it doesn't separate, and so those guys have to stay together. So I can't cross out anything that's circled, because those are, stuck with each other. But I can look at what's left and see, are there any spectators? The sodium. Here's a sodium ion, and there's a sodium ion. So everybody else got involved in some way, but sodium didn't. So then I'm going to take this one that stays intact and write that HCHO2, aqueous. Here, I don't need the sodium because that was a spectator. I'm just going to write the other ion, so we have the hydroxide ion. And the water needs to be written as a molecule. And then over here, sodium was a spectator, so I'm just going to write the anion. And that's my net ionic equation. Any questions? We'll be doing a number of titrations in lab. A titration is just a technique in which we take a substance in solution where we know the concentration, and we react it with another substance in a solution where we don't know the concentration. And the point of it is to find the unknown concentration. So we'll add one solution to the other until the reactants are just right, until it's a stoichiometric ratio. That's called the equivalence point, where we don't have an excess or a limiting reactant, we've got them just right. And at that point, knowing the concentrations and the volumes that we've added, we can calculate what the unknown concentration is. And these are stoichiometry calculations with solutions. Well, the trick, of course, is how do you know when you've added a stoichiometric amount? Well, when we do this with an acid and a base, we can use an indicator. An indicator is generally an organic compound, is often a dye, and it changes color in response to the pH of the solution. So if the solution is acidic, it's one color. If it's basic, it's another. If there's an excess of hydrogen ions or an excess of hydronium ions, it will change color. And so we can use that as a visual indication that we've added the right amount. So at the equivalence point for an acid-base reaction, the number of moles of hydrogen ions is equal to the moles of hydroxide ions that were added. So here's an illustration and some pictures. So here we're just looking at this net ionic equation of hydrogen ions plus hydroxide ions to form water. This is actually a sodium hydroxide solution and a hydrochloric acid solution, but the sodium ions and the chloride ions are spectators, and so we can just kind of ignore them. So here we have a burette holding hydroxide ion solution, the sodium hydroxide. The burette is great because we can add varying amounts in a very controlled way and still measure the volume accurately. So we're going to add a little bit of sodium hydroxide to this flask where we have our acid solution. Typically, the known concentration is in the burette and the unknown is in the Erlenmeyer flask, but sometimes we do it the other way. So here we have the hydrogen ions. So we're going to add some sodium hydroxide, some hydroxide ions. Those hydroxide ions are going to pick up these hydrogen ions and react and form water. That's what this net ionic equation is telling us. So we will keep adding those until the solution turns pale pink. Because when that has happened, we have neutralized, we have reacted all of the hydrogen ions that were in the solution. And we've got just the right amount at the equivalence point. Now, actually, we typically go a teeny tiny bit over, but it's still close enough. So when the color changes, we call that the end point, and hopefully the end point and the equivalence point are really, really close together. I'm just seeing that in this sentence here, there's this extra parenthesis. I'll have to fix that. So this is what it would actually look like. You have a colorless solution and a colorless solution, and as you're adding the sodium hydroxide, you'll begin to see a little bit of pink here because the solutions haven't mixed yet. And so in that local area, there's an excess of hydroxide and it turns pink. When you give this a swirl and mix it, it will go clear again. And we're going to keep going until the solution turns pink. Now they went way overboard here so that you could be sure to see that it's pink. That's actually way too pink. If you keep adding sodium hydroxide, all that will happen is that it'll get darker pink for a while and then it'll just stay that way and you can just keep adding. But when you go past the equivalence point, then it's not useful at all. It doesn't mean anything. So there's no point in doing the titration if you're going to go past the equivalence point. Any questions? Did you guys do titrations in your previous chemistry class? This is yes, this is no. So a mix. Well, because I'm getting a lot of, and that doesn't give me any information at all. So I understand nobody's going to actually, stand up and tell me about it. Just little nods and shakes. Okay, so mixed bag. Some have, some haven't. Okay, we're going to do a calculation here. A titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What's the concentration of the unknown H2SO4 solution? This is solution stoichiometry. So we need a balanced chemical equation. So we've got H2SO4 and we've got KOH. So those are our reactants. We don't really need to worry about whether they're aqueous or solid or liquid or anything. We can just leave the state symbols out for these reactions. So I've got H2SO4, and that's reacting with KOH. And what I need is I need to know the mole ratio between these two. So I need to make a balanced chemical equation, and I'm going to do that by swapping partners here. So sulfuric acid has two ions, hydrogen ions and sulfate ions. Potassium hydroxide has potassium ions and hydroxide ions. And I'm going to swap the partners. And over here, I'm going to get H plus and OH minus. which hopefully, this is becoming familiar. That's H2O. And I'm going to get the K plus and the SO4 2 minus. This has a -2 charge, this has a +1 charge. So writing the formula, K2SO4. Some of you did really well on your nomenclature worksheet. Some of you need some help. Okay, so be sure to look at those graded worksheets because you see what I just did here. We have to be able to take ionic compounds apart into separate ions and put them back together again, or we're going to be sunk. Okay, I do not need my little notes down here anymore. I don't have to write a net ionic equation. I am going to need to do some calculations, so I'm going to erase that. That was the process in how I predicted the products. I do need to make sure that this chemical equation is balanced, is it? No. So you can kind of eyeball it and look at it, and I'm seeing that there's 2 Ks here and only 1 there. So I need to put a 2 in front of KOH. That gets me 2 potassiums on each side. The sulfate stayed intact. I have an SO4 there and an SO4 there. And so now I need to look at the hydrogens. There's 2 hydrogens, and this one has 2 hydrogens. Over here in this one water molecule, I only have 2 hydrogens, so I need to put a 2 here. So I've got 2 oxygens not in the sulfate and 2 oxygens not in the sulfate, and so it's balanced. There's different ways to go about that. Here's a clue, kind of a tip. So this is a diprotic acid. It's H2SO4. That's going to need 2 hydroxides. And this is a base that only has 1 hydroxide. So we're going to end up with a 2 in there. Okay, I've got my balanced chemical equation. Now I'm going to take my numbers and write them under so I can organize them. So I've got 20 milliliters of the H2SO4. 20.0 milliliters of that. I've got 22.87 milliliters of the KOH, and they told me what the molarity was. Always write molarity as moles per liter. A common mistake is to write capital M thinking that that's an abbreviation for mole. It is not. Mole is MOL, lowercase. Capital M means moles per liter. So I've seen capital M divided by liters. That's moles per liter squared and doesn't make any sense at all. So watch out for that. Okay, can we use the dilution equation? Are we diluting something? No, we have a chemical reaction. I've got 20 milliliters of this thing, and I've got 22.87 milliliters of a different substance. Do not use M1V1 for acid-base titration. And if a tutor or someone else tells you to do that, I want their name, okay? Because I'm going to go, I'll be nice, but that's bad advice. Okay, so this is stoichiometry. Grams to moles to moles to grams. General path for stoichiometry. And then we just have to look and see, are we switching it up? So what do I have to start with here? I've got milliliters and I've got a molarity. So I'm not starting with grams. I'm going to start with milliliters. And then at the end, what am I trying to find? The concentration in moles per liter. So do I need grams at the end? No. I need moles, and then I'm going to divide the moles by the volume in liters to get the molarity. So I'm really doing milliliters to moles to moles. So then my debate is, do we convert to liters or do we use millimoles? Strong opinion, anyone? Liters? Okay, we'll do this one with liters. Okay, so I need to convert these milliliters to liters. So this is such a common conversion that you really should learn how to do it. Milli is 10 to the minus 3. We're going to move the decimal point 3 places. Bless you. The question is, what direction? And so use a little bit of common sense. We've done stuff in lab. How big is a milliliter? Just show me with your fingers, right? It's a little bit, right? It's this little, it's a square, cubic centimeter, right? Little tiny bit. How big is a liter? How big is 2 liters? You know how big 2 liters is, right? 2-liter bottle of soda, right? Okay, so if I have 20 of those little things, is it 20,000 liters? No. It's 0.02 liters. So I need to move the decimal point 3 places, and my choice is to move it to the left, 0.0200 liters, or to move it to the right, that's 10,000 soda bottles. Is that 20 milliliters? No. Okay, don't do that. So we should be able to figure that out. Just a little bit of thinking. So 22.87 milliliters, that's 0.02287 liters. Okay. You can write it all out with the times 10 to the minus 3 if that is necessary. Okay, so I'm starting with, I changed this to liters, but I'm starting with liters of potassium hydroxide because that's what I know about, and I'm trying to find the molarity of the sulfuric acid. Question mark, moles per liter. So I've got 0.02287 liters of KOH. And I'm going to convert that to moles of KOH. And liters will be in the denominator. And then I'm going to convert that to moles of sulfuric acid. And moles of KOH will be in the denominator. So I'm getting my units to work out here. The mole ratio comes from the balanced chemical equation that I just wrote. 1 mole of sulfuric acid reacts with 2 moles of potassium hydroxide. 1 mole of sulfuric acid reacts with 2 moles of potassium hydroxide. This is the molarity that was given, 0.158 moles per liter for the KOH. So I've got my volume to moles, and then I'm going to figure out my moles of H2SO4, and then I'll divide. 0.02287 times 0.158 divided by 2. I want to keep a minimum of 3 significant figures here. Remember, those leading zeros do not count. There's 3 sig figs, and I'm going to write down 2 extras because that's what I do. That's my moles. I'm trying to find the concentration. So I want the molarity. That's moles of H2SO4 divided by liters of the H2SO4 solution. So I calculated the moles, 0.0018067, and I divide by the volume of that solution. This is the volume of the solution that had that many moles in it. So I divide by 0.0200 liters. So there's my number. Should have 3 sig figs. So when I round it, it should be 0.0903 moles per liter, or 0.0903 capital M. Any questions? Yeah.
If you were titrating with a weak acid, would it still be the same process?
That's an excellent question. What if it was a weak acid? If it was a weak acid, it would still be the same process. Because what happens is the weak acid ionizes a little bit, and the hydrogen ions that have ionized get reacted with sodium hydroxide. And so then you're left with the molecules, but they will ionize a little bit still. And so they will just ionize as the hydrogen ions get used up. So in terms of acid-base titrations, it's exactly the same. Where we need to be careful of it is just with those net ionic equations. So that was the neutralization reactions. What about the gas evolution reactions? We can get a gas formed in a reaction 2 different ways. Sometimes we get the gas forming directly. We'll get an ion exchange that results in a gas. So here we have potassium sulfide and sulfuric acid. So you swap the partners and you end up with potassium sulfate and hydrogen with sulfur. Well, H2S is a gas. How do you know that? Well, I just told you. So now you have to remember. H2S is a gas. It kind of looks like an acid, doesn't it? Well, it is an acid, but it doesn't dissolve in water very much at all. It's a weak acid, and so it's mostly going to just bubble out of the solution and smell really bad. We can also get a gas forming when our exchange reaction forms something that's unstable. So sodium bicarbonate or sodium hydrogen carbonate, that's baking soda, reacting with HCl, hydrochloric acid. It's going to produce sodium chloride and carbonic acid. Carbonic acid is unstable, and you're going to know that because I just told you, and now you have to remember it. Carbonic acid is unstable. It decomposes, and it decomposes to form water and carbon dioxide. And I think we all know that carbon dioxide is a gas. So here we've got sodium carbonate, sodium hydrogen carbonate getting poured into HCl, and a lot of bubbling and fizzing occurs. The carbonic acid gets formed and it immediately starts to decompose and produces carbon dioxide. When we do titrations in the lab, what we end up with are wastes that the only thing that's dangerous about them is that they might be acidic or basic. And so instead of collecting all of these hazardous wastes and needing to expend a lot of money and energy in treating them, we'll just make sure that the solutions are neutral, and then they are just salty water and we can dispose of them in the sink. And so when we have leftover acid, we will neutralize it by adding baking soda. And you know it's done when the fizzing stops. Then you know you've neutralized all the acid. Okay, so these are the 4 different reactions or types of reactions that you need to recognize. So this first one, when you react something with a sulfide and you get H2S as one of the products, you need to remember that's a gas. These other 3, we just looked at H2CO3, so carbonic acid. That will decompose and form CO2. There are 2 other compounds that we need to remember: H2SO3, sulfurous acid, and ammonium hydroxide. And they both decompose and form a gas. Now that may seem pretty complicated. Actually, what you just need to do is remember H2S is a gas, and remember these 3, and I'm going to show you how you can figure out what they make. So what these do is they decompose and they give off a water molecule, and then the gas is everything else. So if I look at the H2CO3, so that's going to decompose and form a water molecule, and what I do to find out what the other formula is I get rid of the two hydrogens, so those would be gone. And I've got the CO3, and one of the oxygens is going to go with the water, and so what I've got left is the CO2. Maybe I'll write it over here. So that goes with the water, and one of these goes with the water, and so I'm left with CO2. Same thing happens with these other two. So H2SO3. A water molecule is going to come out. So I've got H2SO3. So two of those two hydrogens are going to go to the water molecule, and one of these oxygens. So instead of 3 oxygens, I'm going to have 2. So that's the formula for the gas, SO2. Ammonium hydroxide does the same thing. Bless you. It's going to form a water molecule, and I'm going to put the other stuff together. This might be a little harder to see, NH4OH. So that oxygen's going to go away, and I need to get rid of 2 hydrogens for the water. So this hydrogen, and I have to get rid of one of those. And so that's going to make ammonia gas. So when you're predicting the products of a reaction, you separate them into ions, you swap the partners, you put them together, you see what you've got. Do you have things that are insoluble? Okay, those are solids. Now we need to check, do I have one of these? Then I need to continue and show what that decomposes into. Do I have H2S? That's going to be a gas. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. They didn't give me the formulas, so I'm going to start by writing the ions. Hydrobromic acid, is that an oxyacid or the other kind? It's the other kind. The prefix hydro means I've just got hydrogen and bromine. So that one's H plus and Br minus. So when I put those together, I've got HBr. And I've got potassium sulfite. So potassium is K plus, sulfite is SO3, 2 minus, because you memorize it. It's the light version of sulfate. That's K2, SO3. And now we're going to predict the products by swapping partners. We put potassium and bromine together, and hydrogen and sulfite. So I've got K plus and Br minus. I've got H plus and SO3, 2 minus. So potassium and bromine would make KBr. This would be aqueous. Hydrogen and sulfite, I need 2 hydrogens, so I'm going to get H2SO3. And we should say, oh, that looks familiar. That's one of those 4 things we need to remember. This is unstable, it decomposes. So it's going to decompose, and it's going to form water, and what's left from that molecule when I take 2 hydrogens and an oxygen off? SO2. So instead of writing this unstable thing, I shouldn't do that. I'm going to write the H2O plus SO2 gas. Any questions? you can pass the class if you don't remember the gas evolution reactions.